present.
Hi, yeah, and this is joint work with my collaborators Dan Licata and Amal Ahmed. So this is another talk about gradual typing, of course. And so the perspective I want to emphasize is that gradual typing is about adding types gradually to make the types in a program more precise over time. So you might start out with a prototype or legacy code that's dynamically typed, and gradually add static type information to it to increase performance or maintainability. And to take a somewhat real-world example, Twitter was originally written in Ruby on Rails, and they found that it didn't scale to the massive amount of users that they had. So they decided to rewrite a lot of the website in Scala. And this is great. Scala is a great language, but if you do this in a naive way, this could take a really long time. If you had to rewrite the entire application before you were able to deploy again. And so what you need to do instead is re-architecture your application so that Ruby components can interact with Scala components. It's a little complicated. And to boot, you can introduce bugs in the translation process. Instead, if they started with a gradually typed language like Racket, they could have gone piece by piece, module by module, adding type annotations and doing much less extensive rewriting, and then eventually maybe getting a fully typed program. But the point is, in gradual typing, when you add types to a module, it's a drop-in replacement for the dynamically typed program. And so at every point in the middle, you have a running program. But then the problem is, the question is, how do these programs in the middle actually run? And so the way that we formalize this is we'll usually embed the dynamic and the static languages into a combined cast calculus. And then we'll have to insert these typecasts at the dynamic boundaries. So for example, if we have a function f of type arrow b, and I have a dynamically typed input x, where I'm using a question mark as the dynamic type here, then in order to apply f to x, I'll need to first cast x from dynamic to a. And then the question is, how do these casts actually run? And this one is a little complicated if you go into the gradual typing literature. And so even for just the simple types, there have been many different proposed semantics. So there's erasure semantics, which is basically just run it as a dynamically typed program. What I call wrapping semantics, which is the most standard, which goes back to Fendler, Fleiss, and Contracts in the Seek Taha paper. There's eager semantics, which tries to catch type errors earlier than the wrapping semantics would. And there's transient semantics, which tries to reduce the number of casts by delaying some of them until later. And so, if you're going to design your gradually typed language, you probably look at this and you say, well, which one of these semantics is right in some sense? Which one is the one that I want? And so we like to argue about this in our papers, and the way we usually argue it is through things like type soundness theorems, right? And so you go to these papers and they go and they define their operational semantics, they do a bunch of proofs, out pops some soundness theorem, which they argue gives you good properties of the language. But as language designers, really we should be thinking about these soundness theorems first, and then designing the semantics based on that. And in practice, that's what we do. And in this paper, we try to make that into a more formal process. So instead of the operational approach, we're going to take an axiomatic approach to gradual typing. We take desired soundness theorems for gradual typing from the literature. We axiomatize them into type theory, and then in that type theory, we can prove operational reductions are program equivalences. And this actually turns out to be a stronger theorem than the operational approach, because what we have is that since we can derive that the operational semantics has to be the wrapping semantics, this means that the wrapping semantics is the only one that satisfies the soundness theorems. And I'll go over what those soundness properties are in a minute. Okay, so that brings me to the contributions of our paper. So we develop a novel type theory that axiomatizes gradual typing, which we call gradual type theory. It's based on Levy's call by push value. And then we derive these reductions in the type theory. And to show some generality, we should derive semantics for both call by value and call by name evaluation orders. And so a few of the reductions are not totally determined by the axioms, and for those we give multiple operational models, and we prove them sound using a logical relation. Okay, so for the rest of the talk, first I'm going to say what these soundness principles are that we want, then I'll describe how we axiomatize them in gradual type theory, and talk a little about how we derive the semantics. Okay, So what are these principles of gradual typing? What should a gradually typed language be like? Well, number one, a gradual typed language should be gradual. And by that I mean it should satisfy a property that I like to call graduality. And this was originally proposed as something called the dynamic gradual guarantee in this nice paper by Seek, Vitusek, Chimini, and Boylan. But I like to call it graduality in analogy with the parametricity theorem from polymorphism. And the basic idea of graduality, if we go back to our picture from earlier, is that as I'm adding type annotations to my program, I still have the same underlying code. And so I should be able to understand the behavior of the more typed code based on the behavior of the dynamically typed code I started with. And more specifically, we want to say that the statically typed code refines the behavior of the more dynamically typed code, in that it either has the same behavior or it reduces to a runtime error because it's enforcing more precise static type, or static and dynamic types. And so to formalize this, just as we saw in the previous talk, we have to have a type precision relation where something on the left means it's more precise, something on the right means it's less precise, which is a little confusing. But the rules, as we saw last time, are that the dynamic type is the least precise type. It's an ordering, so it's reflexive and transitive. And then every type constructor is monotone with respect to this ordering in every argument, including here the function type, which is monotone in the domain. So this is not your normal subtyping. And then from that, we extend the type precision relation to a term precision relation, where we say that T is more precise than T prime if they have the same underlying code, and every type in T is more precise than the corresponding one in T prime. So we think of T as the result of making the types in T prime more precise. And then the graduality theorem is that if T is more precise than T prime, either T reduces to a type error, in which case we don't know anything about T prime's behavior, or otherwise they have the same behavior. They both diverge, they both reduce to values, and then you can extend this easily for other effects. Okay, so gradually typed languages should be gradual, so you might guess that gradual typed languages should also be typed, soundly typed, that is. And so one thing that you might think is that well-typed programs cannot go wrong, but of course gradual typing includes dynamic typing as well, so this is going to be insufficient for us. And so usually we'd prove some kind of syntactic type safety theorem where the progress theorem includes a type error. But in this study in our paper we go further and we say, you know what, types should provide relational reasoning principles, equational reasoning principles, and the ideal would be the gradual types should provide the exact same reasoning principles as the static types, relational principles. And so the one we're going to focus on is eta equality. And so what is eta equivalence? Well, I hope you are a little familiar with it, but eta lets us reason about programs just from their types. So these are the original free theorems. So for instance, for function types, the eta law says that anything of function type is equivalent to a lambda term. But actually every symbol type has a corresponding eta principle. So for instance, the eta principle for Boolean says any term with a Boolean input is equivalent to a term that immediately does an if statement on it. And then does true in the true branch and false in the false branch. And you might be squinting at this first one and say, hey, wait a minute, that doesn't actually look right. And that's because eta is effect sensitive. So we need to be careful about the evaluation order when we specify these. So for instance, for the function type, this one's going to be true in call by name evaluation, but false in call by value, because a diverging program will not be equivalent to a lambda. But this is not hard to fix. We make what's called a sort of value restriction. We say, well, the eta principle is true, but only for the pure terms or the values. And there's actually the exact dual problem for the Boolean case. This one's true in call by value, but false in call by name. And so with a similar problem, if you give it a diverging input, and we can apply a dual restriction, which says that the eta law for Booleans is only true if the program using it is actually strict in the input, or more specifically, linear. Okay, so those are the principles that we want. Now how do we actually add them to our type theory? So we're going to make this type theory gradual type theory, which has gradual types and casts. and it's going to axiomatize these principles, and it's going to include both call by value and call by name. And the way that we accomplish that is we base it on a calculus called call by push value, which was introduced by Paul Blaine Levy. The main thing you need to know about call by push value is that call by value and call by name embed into it. And the slogan here is that these embeddings are subsuming, which means basically they preserve everything you could possibly want. The operational semantics, the equational theory. So anytime you want to prove something about call by value or call by name, you can pretty much always prove it in call by push value instead and get them both for free. And just a few basic ideas from call by push value. So call by push value is effect sensitive, so it distinguishes between 3 different kinds of terms. There's the generally effectful terms, which are called the computations. Then there's the pure values and the linear stacks, which are the same ones that we saw in those restricted eta laws. And then there's 2 kinds of types. There's the value types, which classify first-class data that can be passed around, like Booleans and strict tuples. And then there's the computation types, which classify program behavior, like functions and lazy pairs. And then the main thing you need to understand is that the call by value types are embedded in the value types, and the call by name types embedded in the computation types. Okay, so then gradual type theory extends call by push value with features that axiomatize gradual typing. So specifically, we first, to axiomatize the graduality property, we add precision relation. And the main thing to know is we add a different relation for everything. So we only compare value types to value types, computation types to computation types, etc. And we add reflexivity, transitivity rules for all of them, and congruence rules for all type and term constructors. Then we add dynamic types to the system. And there are a few different choices that we explore in the paper, but in general, we can have a dynamic value type and possibly also a dynamic computation type. And the way we add them is we just put them both at the top of their corresponding kinds. So they're both the most imprecise types of their kinds. And so we can think of the dynamic value type as we normally do, as kind of like S expressions, dynamically typed data. And the dynamic computation type is more like a kind of dynamically typed object, like something that can be sent any message, but possibly fail. Then we add the type error, and to axiomatize the graduality property, we put the error as the least element of this ordering. And then to add the beta and eta laws, we just add them as order equivalences. So we add less thans in both directions to add it as an equality. Okay, and then we finally get to the typecasts. So the first question we have is typecasts are terms, so we have to decide what effects can they have. Should they be values, computations, stacks? And so we show in the paper that the only really valid choice is that when we have an upcast, i.e. less precise or a more precise type being cast up to a less precise type, then it actually turns out to be a pure value, which is trivial in call by name, but interesting in call by value. And then we get a dual property for the downcast, which is that the downcasts end up being stacks, which is trivial for call by value, but useful for call by name. And so this observation should be useful for optimizing gradually typed programs, because these 2 analyses, purity and strictness analysis, are 2 of the most common in optimizing compilers. Okay, so now how do we actually specify the behavior of these typecasts? So normally at this point, I would throw a bunch of operational rules, and you'd get a bunch for each type. But that's not what we're going to do today. Instead, we're going to sit back. We're going to say, OK, how should these casts behave? And the intuition that we have from this graduality theorem is that when I cast a term, it should behave as much as like the original term as possible while inhabiting the new type. We can formalize this using the term precision relation. So for instance, when I have a downcast, so I have b is less than b prime. Now, when I have a term m of type b prime, and I cast it down to type b, it might not have the type b, so it might error more than the original term. So it should be it should be more precise than the original term. But this would be satisfied by even saying that all casts should error all the time. So we want to make sure it's not too small in the ordering. And so the way we can do that is to say that actually it's the greatest term with this property. And so we can define the downcast by saying that it forms a kind of greatest lower bound on the original term. And then we can do an exactly dual construction for the upcasts. So when I upcast a value, all errors that are in it should be in the original value. And it shouldn't add any behavior where there was an error before, so it should be a least upper bound on the value. So instead of all these rules and adding new ones for every type constructor, we have a simple specification where there's only 4 rules all in all for all of the casts. Okay. And then to sort of summarize, the way that we axiomatize gradual type theory, we add this precision relation, and then we really specify all the other constructions using order theoretic properties. Dynamic types are least precise, type errors most precise, and the casts are least upper bounds and greater slower bounds. Okay. And now I'll just talk a little about the actual theorems that we prove in the gradual type theory. So what we can prove is that for every type constructor in call by push value, that the downcasts between types that have the same connective are equivalent to actual program implementations. So for instance, if I downcast between 2 function types, then I can prove in the theory that that's equivalent to the function that takes in an input, upcasts the input, runs the function, downcasts the output. So the classic function contract, and basically what you would come up with if you were asked how to implement this function. And then we can prove it for every type. So for instance, for products, the upcast should be that you split it apart, upcast each side, and then tuple it back together. And then because these are theorems in gradual type theory, which axiomatizes the graduality and eta principles, we know that any semantics that is observably different from the wrapping semantics must violate some eta principle. So the eager semantics is a bit over-eager on functions, and it breaks the function eta principle. And the transient semantics is too lazy on strict tuples, and so it breaks the pair eta law. But the wrapping semantics gets it right. Okay, so there's a lot more in the paper. We show concrete counterexamples to those, and we give some implementations of the dynamic types, and we prove them all sound using a logical relation. And there's more proofs in the online version on arXiv. Okay, so to wrap up, one of the things we want to consider is, can we use the same sort of approach to derive more advanced cast semantics? So recursive types we think should be pretty easy, but more complicated types are harder to say. And part of the problem is, we don't have as good as canonical of an idea of how to axiomatize things like state and polymorphism. And then the other question that I have is, the eta equivalence determines the wrapping semantics. Can we come up with equivalent not equivalent principles, but principles that determine the other semantics? So that determine, how do we optimize these other programs? Yeah, and this is especially useful because eta is violated by things like object equality of functions, which is very common in dynamically typed languages. So it'd be useful to characterize reasoning principles there. So just to conclude, we've axiomatized the gradual typing principles in our type theory. We use order theory to give them very simple specifications. And the axiomatic approach lets us kind of explore the design space and prove sort of this general no-go theorems. And the equational approach to soundness, I say, would be the key to that approach. So yeah, thank you.
We have plenty of time for questions.
So it's nice that you check that you preserve eta laws, but you began by saying, well, we can't use well-typed programs don't go wrong. Of course, going all the way back to Findler and Verleisen is this idea of saying well-typed programs can't be blamed.
Yeah.
Right, and the notion of blame is very useful if you've got a client and a server, it tells you which one violated things. So can blame fit into what you're doing?
Yeah, so blame certainly fits in. I think I wouldn't know how to derive something from the blame principle because it doesn't give you program equivalences like the eta principle does. But the way that we use upcasts and downcasts, I think, plays very nicely with the characterization from your paper with Robbie Findler about the upcasts only blaming one side and the downcasts blaming one side. I think that's very closely related with this observation that we have about the upcast being pure and the downcast being stacks. I think there's a real kind of
Okay, so I look forward to the journal version that brings out those relationships.
There's a little in the paper. We do talk about it a little.
Really cool stuff. Have you had some thoughts about how to exploit these equivalences to say do like cast optimization, like where you could have certain ones disappear altogether rather than being factored in the usual way?
Yeah, so certainly you could, this kind of gives an equational theory of the casts. And so we could use it to justify the correctness, to prove the correctness of an alternative like space-efficient semantics by showing that those behaviors are equivalent to these behaviors. Because this one gives this sort of naive, like for space reasons, semantics, but extensionally, these determine the semantics. So I think it could be used for that, yeah.
I have a question. It's a really cool work. I see it as you taking on sort of two of the big dichotomies in language design. That's call by name and call by value, static and dynamic, and addressing them all together. It's really cool. My question is, you're looking at eta equality, which is nice, but it's a very fine notion of equality. Can you have more liberal notions of equality and get something else out of it, beta, eta, perhaps?
Well, we do use beta eta equality.
It's just eta, right?
Well, I'm just emphasizing eta because beta will be true even in a dynamically typed language. And the eta laws, yeah, they give you this extension, the more type-based reasoning principles. But yeah, we have beta and eta in there. Okay. Yeah, sorry.
Is this on? Okay. Thanks. This is a bit a question about the presentation of gradual typing. Would it make sense to just think of sets of types instead of having this question mark? The type error would then just be the empty set of types. And then you could see the static typing as just an optimization. If you have a singleton set, then you can remove the tags. I mean, this is maybe a question to the whole community of gradual typing.
Well, I'm not quite sure what you're saying. It sounds quite similar to the abstracting gradual typing approach that is used in the previous talk and the next talk. So you might want to look into that.
All right, let's thank the speaker.